Electric circuit. The goal of this exercise is to illustrate on a bounded error estimation problem the principle of constraints propagation, how it works, why it is easy, and why it is efficient. So for this, we consider an electric circuit with one battery and two resistors. We have some information due to some measurements, and we know, for instance, that E, I, U1, U2, and the power delivered by the battery P belong to some intervals. But we don't know anything about the resistors R1, R2, and from all the physical relation we have between these variables, we want to find an interval for R1 and R2, so the set of all possible values for R1 and R2 that are consistent with all intervals for other variables, but also it should be consistent with all the relations between these variables. So the first thing we have to do is to give the relations that link all these variables. So for this, I have this electric circuit, and I know that, for instance, here, for instance, we know that U2 is equal to R2 times I. This is due to the Ohm rule. We also know that U1 is also to the resistor R1 times the current I. If we add a new variable, for instance R, which corresponds to the equivalent resistor with R1 and R2 in a serial configuration, we have R equal to R1 plus R2. In this situation, I will be able to write, for instance, that the power P is equal to E times E. So the voltage at the bounds of the battery. We also know that E corresponds to U1 plus U2, and we know that U equal to R times E. We also know that the power is equal to R times E squared, and so on. So you should understand that all these constraints are redundant. I mean that from some of them I am able to prove some others. And it is what we have in practice. When we have a complex experiment, we are able to write many constraints relating these variables, but we are not sure that they are independent. But here we don't care. We add all the relation. We are sure the system that links the variables inside the system. So for all these variables, I will have some domains which are given under the form of intervals. So I will know, for instance, that U1 belongs to an interval U1. I know nothing about R1. So R1, I will say that it belongs to minus infinity plus infinity. or if I know that it is a resistor, so it should be positive, so maybe I can put 0 here, if I know it, of course, and so on. And these variables are given here. So for U1, for instance, it was 10 and 11. So here it was between 10 volt and 11 volt. So and so on. Now I will build to perform the resolution for each of these relations. So this one links 3 variables and it will be associated to the multiplication, here to the addition, to the multiplication, and so on. So I will build the contractor corresponding to each of these relations. So for this, I will go with Python. I will take, for instance, the math myInterval.py, and I will save as let's say my contractor. .py. So of course I will not need all this, so I will remove many of them. So I will remove this, for instance. I will keep okay, I remove many things. Okay, I keep import math. I will import interval. So from my interval, import all. And I will build the contractor associated with the addition. So I will call it C-add. This contractor will have as input Z, X, and Y. This contractor is associated to the relation V equal X plus Y. So you should see here that I have kept the order. So here Z appears the first, then X, then Y, and I will keep it here. So now let me recall how it works for the contractor. If I have a constraint, let's say Z equal X plus Y, then I know that also X belongs to X, Y belongs to Y, and Z belongs to the interval Z. Then I will know that Z belongs to Z intersected by X plus Y. I also know that X belongs to its domain X, but also belongs to Z minus Y. I also know that Y belongs to Y, but also belongs to Z minus X. This corresponds to the new domain for Z, for the contracted domain for Z. This corresponds to the contracted domain for X, and this one for the contracted domain for Y. Now I will program this contractor. So I will have to return the contracted domains z intersected by x plus y. So these are intervals, of course. It is for the first one, for z. Then for y, for x, I will return x intersected by z minus y. And for the last one, y and x. So this corresponds to what I have written here. Let me check this. I will take an interval a, which inside, for instance, this interval, an interval b here, so I will take, for instance, 3 and 4, and here 5 and 20. Print c equal c, so a equals to a, b equals to b, and c, I will write c, and I will write this before the contraction and after. So I will write z x and y equal c add of z, c a and b equal to c add c a and b. Then and after the contraction I will write them once more, and they should be contracted. One comma here. Here it's y, x. So the contraction is given here. A has been contracted, B has not been contracted, and C has been contracted. So it seems to work. I will have also to program the same for the multiplication. So for the multiplication, I will build a contractor C mul. I will return the same, but here it will be multiply, here the division, and here the division. So I will not check it, but I can also program some other contractors, for instance, the exponential, just to multiply, just to show how it works. About the multiplication, the exponential, I will enter y and x, and I will return, so y divided by exponential of x, and x intersected with the logarithm of y. I will check that they have been implemented. Here in my interval, I see the logarithm and the exponential have been implemented here. Okay, so now last one, which could be a little bit more complicated, and I will need it because I will need the square. Why? Because here I need the square at this level, p equal r times I square. So about the square, how will I square x and y? And I will return two intervals, and I will now explain how I will have to do. So I have my square function. I draw it here. Oops. And I recall that for the square function, if I enter a box like this, it should be contracted by a box like this. If I enter a box like this, then it should be contracted as follows, and so on. Maybe the last one, if it encloses 0, let's say if I take one box like this, it should be contracted by a box like this, and so on. So how will I do? I will decompose my function into two blocks, the left part and the right part, and I will bisect on the right. So I will if I have a box like this one, like the green one at the bottom, I will cut it into two parts. So I will cut it into this direction. I will have the left box and the right box. I will contract with respect to the right part of the parabola, and the left one with respect to the left part. And then I will make the union at the end. That's what I will do. So here x1 equal to the x intersected with the interval minus infinity 0. So it is the negative numbers. It corresponds to the left part. x2 the same, but 0 plus infinity. Then I will compute y intersected by the square of x1. But I will also compute this one intersected by the square of x2. I will obtain two intervals, this one and this one. I will make the union, and this will correspond to the contraction with respect to y. Two things may happen if y is empty. If y is empty, I should return the empty set for x, but also for y. So empty here is y and y. So I return empty, empty. Else I will compute x1 contracted, so it will be x1 intersected by, so I will start with, do the same also with x2, and x2 is more easy, so intersected with the square root, so the backward function of y, but here it will be -1 times the square root of y. And it will correspond to x2, sorry. Then I will return at this level y and the union of x1 and x2. Here y equal to the square of x as a command. So let me check this. If I have this for a, b, I will c square so b a b a. I run it. Oops, it tells me that the OR operator has not been implemented in intervals. So indeed here I have the AND but not the intersection, but not the union. The union or overloading. So this will correspond to the OR, so it will the union of intervals. Union, whereas this one corresponds to the intersection. So if x is empty, I will return y. Because the union of x and y will be y. The same, if y is empty, I will return x. Else, I should return an interval with the mean of the lower bounds and the max of the upper bounds, which corresponds to the union. square t is not defined also. I go to my interval. Indeed, square is here, but not the square root. Square root. I will do x equal x intersected. So I first intersect it with a negative number, a positive number. Then I return the image of this intersection. Okay, interval of mat dot square root of x dot lower bound. I remove this, and I will do the same for the upper bound. Okay, the square root is now implemented. So the initial value for A was here, for B was here. I have the contraction for A, and B is not contracted. I have done the question number 2, and now I will have to compute an intervals for R1 and R2 by taking all these domains into account, but also the relation I have found in question number 1. So I will take this one, file save as. I will call it, for instance, my circuit. I don't need math. I will need my contractor. I will import all. I don't need this. Okay. First, about the resistor R1. R1 is an interval which is between minus infinity and 0, let's say, plus infinity, because it is positive. R2, the same. I have all the variables I have to put are those that are involved here. So for instance, P, R also here have to be initialized. For instance, R, I will take intervals of, I could say 0, but I can put also minus infinity, for instance, because with the relation R equal R1 plus R2, it will immediately contract it to 0. Anyway, E is an interval which is between 23, 26. I is an interval between 4 and 8. U1 is an interval between 10 and 11. U2, an interval between 14 and 17. P is also measured. The power is between 124, this one, and 130. Okay. Now I will print all of them before the contraction. So I will do print R1 equal 1, okay, R2, R2, R I don't need it, it's E, E, I, I, U1, U1, U2, U2. So it is before the contraction. Now about the contraction. I will do R, R1, R2 equal C add, so the contractor for the addition of the three of them. It is due to the fact that R equal to R1 plus R2. P E I is a multiplication here, simul of this one. The same. P, no, E, R, and corresponds to the Ohm rule. It's a multiplication. I had also U2 equal R2 E. Again the Ohm rule, but only on the resistor number 2. Simul. And also for the resistor number 1, whatever is the order of constraint, we should obtain the same result. And the last one was E U1 U2 C add. So all the constraints I had here have been inserted. Oh, maybe not the last one. I will do it later, the last one. They are implemented here. And then at the end, I will print what happened after contraction. So some variables have been contracted. For instance, U2 has been contracted, R1 also, R2 also, but I could do probably better. So how to do better? I have to perform the propagation several times. So I will do for k in range of 0 and 3, for instance, or 5 or 10, whatever, a large number of times, but here 10 will be sufficient. I will perform all this contraction. So it means that now, since I go to a fixed point, I can permute some of this line. I will always converge to the same fixed point. Okay, so now I have accurate values for R1 and R2. Some of other domains have been contracted. So for instance, I has been contracted also, and so on. Of course, if I add some other constraints, I could be more accurate, but it is not necessarily the case. So for instance, I can add a new variable which corresponds to either in I square, which corresponds to the square of I. So at the beginning, initialize like this, and I will write here c square of I2i, I2i equal, and I will add multiplication. I will say that P equal to R times I2, and if I add this, it is a new constraint, maybe, but maybe not, I don't know. I will be more accurate, but whatever, I will, since P equal to R times I2, I will never lose any solution. Okay, so in this case, I think I have no more improvement, but it could have been the case. More I have constraints, more I will be accurate. I can do these kind of things even if I have many variables. The algorithm is not sensitive with respect to the number of variables. It goes fast. It is a principle of constraints propagation applied to bounded error estimation.